taking class attendance. It's a pattern, so I keep forgetting.
You forget everything.
Okay, welcome back, everybody. Let's just take an in-class attendance. I don't need any avatar. Don't worry about it. I'm going to leave. Okay, that's it. That's it. All right. Come on. Okay.
Oh my God.
All right. So again, updates. So modified and improved edition, 11 a.m. Tuesday, April 6th. Now, of course, the phase 2, this is going to be conclusion of your aerodynamic design. So the next phase, phase 3, is based on your decision. In other words, airplane design is pretty much done. Based on that design, you're going to compute your performance. Performance requires your selection of your power plant and also aerodynamic, which is a drag product. How much thrust is required for given a Reynolds number or flight airspeed, or Mach number if you're a high-speed airplane. And then you're going to also provide thrust available out of your choice of power plant. You're going to plot the thrust or power plot. I assume most of you need a power plot because it's propeller driven. So that means choice of propeller comes into play, propeller efficiency comes into play also, okay? And then, of course, how much fuel do you need? Where do you put your fuel kind of thing comes in, okay? Now, suppose if you put your fuel in a very, very back of the fuselage, that could potentially make your airplane completely unstable. So you have to like double the size of tail kind of thing. So major configuration change may happen at the stage of stability analysis, okay? So at this moment, your airplane's basic configuration come into play. Based on that, you're going to choose your power plant, and you'll try to integrate power plant, and then plot thrust or power curve. And out of those things, you're going to compute performance. Performance include, I don't know what included. Let's just take a look at the documentation. Phase 3, right? Where is it? Oh yeah, phase 3. So phase 3 next to come is like performance computation. So for airplane, so you're going to choose your best airplane configuration out of your team's each individual's design. Then you're going to basically integrate propulsion system, structural material that actually gives you like overall weight of your airplane. And then center of gravity location need to be computed. And also you're going to put the cowling, landing gear, other things, modification, and then weight distribution. You can do that in X-Flyer 5. High lift devices, well, of course, flaps and then control surfaces come into play. If you want to modify wingtip, you can do that too, right? And then all of those, you're going to compute propulsion system thrust or power available, TSFC or BSFC. Propeller efficiency, if you come up with propeller, type of propellers, and the size of it. Specific excess power, this actually gives you maneuvering capability. And then thrust and power and drag curves, this is something you need. And power of glide performance, that is essentially if you turn your airplane into sailplane, what is the maximum endurance, minimum sink rate, or range, okay? And then climb performance, best rate of climb angle, endurance and cruise, and takeoff landing performance. And then other something specific, such as your airplane is something specific to this design, such as SAE. SAE comes up with already the payload. So payload is already constrained. So with this payload, can this airplane even take off and maneuver? That's something you really want to kind of focus on. So you can actually add your performance criteria here on top of this list, okay? Now, SAE, you probably don't care about loiter and range, because all you need is just to take off and barely come back and safely land, not to crash land. That's what you need. Okay, so you can take off some of those listed items for performance if you are specifically designing an airplane for a certain purpose. Okay. So this is now almost like a realistically, am I designing reasonable airplane, or this is, hey, wait a minute, our team now all of a sudden realize this is a piece of crap. Then you go all the way back, phase 1 and 2, reiterate. That's the beauty of your software. Here we go. You don't have to start from scratch, right? You already obtained those data set at the phase 1 stage, phase 2 stage. Okay, so you can always reiterate using computer. That's the beauty of computer simulated design. Okay. Any question here? So let's just to finish up. Fairly good, high quality job at the phase 2. Otherwise, toward the end, you're going to progressively start suffering based on your poor job done at the early stages. Okay? If you do a very, very good quality work, progressively getting more fun. If you just keep minimizing your effort at the early stage, at the very end, you throw everything. A day before a presentation, then presentation becomes disaster. And then professor now has a choice that either should I frank this team or should I just save them kind of thing. Okay, that's a nightmare. You don't want to go through it. Any question? So again, that's why you should probably spend some time doing a good job. This is a Team 5's example. Like I said, this is not the perfect report. I would probably give you 85%. Team 5 is sitting down there. If you're happy with 85%, do nothing. That's fine. You get like a middle B. Again, this is not every, but this team did try to include every item I required you to do. Okay. We talked about some suggested items, such as, especially this one, complete set of 2D data is missing. I want you to include that. Okay. Because if this wing design, you realize this wing design really sucked. You want to go back to the 2D data and then redesign this wing, right? So reiterate. You have to sometimes. Okay, go ahead.
I had a question. So yesterday, or not yesterday, on Tuesday, you were talking about the CM versus alpha plot. So we had CM versus CL plots, and you were saying that you would have preferred CM versus alpha.
CM versus alpha for entire airplane is a trim diagram.
Yeah.
Yeah, we talk about that later.
Yeah.
Yeah.
The thing is, like, I mean, we will do that, but I just, both essentially kind of show the same data.
Yeah, that's right.
Just so I was just wondering, kind of what you thought about that.
Yeah, well, CM alpha actually gives you a trim alpha too, so that actually helps you to size your control surface.
Okay.
So that's fine.
That makes sense.
Yeah. Okay. All right. Good question. Actually, you know what you're doing. Anybody else? Okay, so like I said, this is Tuesday, so just to do your good job. If you want to avoid suffering at the end of the semester, which I really want to avoid it, okay? Because at the end of the semester, all your other classes probably push stuff into your to-do list, right? I don't want to do that in this class. This class, progressively much easier toward the end, having fun kind of thing. Okay, so today we are going to continue on Unit C3, takeoff landing. We talked about takeoff in last class. Let's just to begin with the example C31, page 4. Okay. So takeoff example, page 4. Let's just take a look. This is the non-afterburning turbojet engine of a Cessna T-37 jet trainer, produced approximately 1,700 pounds of installed thrust for takeoff at sea level. Its takeoff weight is 6,575 pounds. It's so accurate. I don't know how you get that kind of data, because this is Air Force Academy. They know those things. Its CL max is 1.6 for takeoff. It's probably fully extended. And its drag polar is in its takeoff configuration is given 0.03 plus. Sorry about that. What am I talking? This is CD. Sorry. This is CD0. This whole thing is CDI. Sorry about that. Yeah, CDI is equal to K times CL squared. Sorry about that. There's a typographic error. Please fix it. So this is CD, not the CD0. Sorry. So CD is 0.03. That's CDO plus 0.057 CL squared. So K is 0.057. Its reference platform area is 184 feet squared. This is wing platform area. S, okay. This is S. Now, normal takeoff procedure requires the pilot to rotate the aircraft to the takeoff altitude just prior to reaching takeoff velocity. You talked about BTO. What's BTO, by the way? Anybody? We assume the BTO is equal to something.
Square root of...
No, 1.2 times V stall.
Oh, yeah.
That's right.
Sorry, I was thinking V stall.
That's a V stall. That's right. You're thinking about equation of V-stall, right?
Yeah.
Yeah, that's right. Random, the only difference is this is going to be 1.3. Yeah. The rest is exactly the same, just the reverse order. Okay, anyways. So, therefore, for the majority of the takeoff roll, the aircraft CL is 0.8. This is quite important. So this is lift coefficient produced during the takeoff roll. This is average, I think. Average. Not the maximum, right? Average. That means when you analyze the actual lift and drag, you are going to consider velocity is equal to 0.7 BTO. Do you remember this also? So this is a takeoff. You're going to start from 0 to takeoff attitude. You're going to keep continuously accelerating. So the drag and lift keeps changing. So in order to represent the average value for lift and drag during the takeoff roll, you're going to pick up the velocity 0.7 times BTO, using that together with average value of CL to figure out lift average value during the takeoff roll. Okay? All right. So what will be the aircraft's takeoff distance at sea level with no wind? Here we go. So let's just take a look at it. This is essentially plug and check, not so bad. So first of all, what is takeoff airspeed, BTO? We want to find out BTO. We know this is 1.2 times V stall.
Dr.
Yeah, go ahead.
Where did you pull the V is equal to 0.7 BTO from?
Oh, it's coming from previous page, right here.
Okay.
Yeah, this signifies that whatever the value within the bracket, thrust and drag and rolling resistance and lift, those values will be computed under the condition of 0.7 BTO, because this represents kind of average value over the takeoff roll. Okay, that's right. Okay, so anyways, let's begin with takeoff speed. So 1.2 times stall airspeed. Stall airspeed is 2 times WTO rho times S CL max. Now CL max is into the equation, not the 0.8. CL max is 1.6 because it's stall speed. So let's just plug in 1.2 times, okay, 2 times weight. Takeoff weight is 6,575 pounds. Density, let's use sea level, 0.002377 slags cubic foot. The wing area is 184 feet square. CL max, of course, 1.6 with fully extended. If you plug in those values to find out takeoff airspeed, this is 164.5 feet per second. So this is takeoff airspeed. Okay. Now, important thing is during takeoff roll, let's find out velocity is equal to 0.7 BTO. This is going to represent the average value of lift and drag and rolling resistance, any other things within the bracket. So 0.7 times this value, 164.5. This is going to give you 0.7 BTO velocity is 115.15 feet per second. Okay? So having said that, let's discover, so out of this velocity, so this actually represents sort of average value during the takeoff roll. What is the dynamic pressure Q? Q is 1/2 rho v squared. So let's just find out dynamic pressure during takeoff roll. 0.5 times density 0.0023 0.77 drag per cubic foot. Velocity is this, 115.15 feet per second, which is 1/2 rho that's square. 1/2 rho v squared, 15.76 psf pound per square foot. This is dynamic pressure Q. So what is the lift for this 0.7 BTO condition? CLQS, okay? CL is, of course, we know 0.8. Q, we found 15.76 psf pound per square foot. Area is 184 feet square. This is going to give you how much lift you are going to produce during the takeoff roll as an average value. 2,320 pounds of lift. Okay. And then we do know CD, this is drag polar, is given by CDO plus K times CL square. CDO is 0.03. K is 0.057. CL, we just found CL is 0.8. 0.8 square. So CD is 0.0665. So this is drag coefficient. So how much actual drag you are going to develop? CDQS. So drag coefficient 0.0665 times Q is 15.76 psf multiplied by the wing area 184 feet squared. So this is going to give you a drag 192.8 pounds. I hope I'm recording. Am I recording?
Probably not.
Yeah, I'm recording. Good for you. Because I feel like I'm the only guy talking. Anyways, if you have a question, just cut right in, okay? I have no problem. So those are the values, okay? Condition is at B, which is 0.7 BTO. Okay? So we computed at condition B equal to 0.7 BTO, you know Q and L and drag. So let's just plug in everything into equation of takeoff distance. Takeoff distance equation. Do you remember this? STO is 1.44 weight of takeoff square rho times S times CL max. G is gravity. Bracket thrust minus drag minus loading resistance coefficient W takeoff minus lift bracket evaluated at 0.7 BTO. Okay, so this is the equation. So whatever inside of this bracket need to be evaluated at the condition of 0.7 BTO. That's what it means. Okay? That's what this thing is. So let's just plug in all of those values here. Okay? So this is going to be equal to 1.44 times weight of the takeoff, 6,575 pounds. Square density is C double 0.002377 drags per cubic foot. Wing area 184 feet square. CO max 1.6. Gravity, of course, 32.2 feet per second square. Okay. So within the bracket, thrust is what? What is the thrust? Do I have a thrust information? Oh, yeah. Produce approximately 1,700 pounds force in all the thrust for takeoff. So let's assume thrust is 1,700. This is independent from airspeed. Okay. 1,700 pounds. Drag is, we found 192.8 pounds minus rolling resistance. What's that? What kind of runway is this? It doesn't say anything. What's the rolling resistance? Let's assume something. So rolling resistance mu. Guess value. Yeah, okay. Where is it? There must be some kind of information for that. Did I say something here? Little bit up. Oh, here we go. Rolling resistance here.
There it is.
Yeah. So 0.02 to 0.04 for paved runways, 0.08 to 0.1 for turf. This is a paved runway. And let's just take the average value, 0.03. Okay, let's just take that mu, 0.03. Okay. So this is a paved runway average value. 0.03 is a mu. W takeoff 6,575 pounds. Takeoff weight minus lift is 2,320 pounds. Okay. Okay. So here we go. So if you compute it, I hope you compute it. This is 2,003 feet. This is takeoff distance. Okay. Now, important thing, alternatively, suppose if your power plant is so strong,
Wait, hold on. Is that 200.3 feet or 2003?
2003, sorry.
Okay.
Let me just write it down once again. It's very bad handwriting.
Okay. Thank you.
It's just yeah. Okay.
Worse.
Ah. So 2,003 foot. 2,000 feet. Well, I mean, it cannot be 200 feet, anyways. 200 feet. No.
Yeah, I mean, yeah, 203 feet sounds pretty short.
Sounds crazy.
but-
You need
Yeah.
a very weird airplane. Maybe airplane comes with like a parachute or something. You can do that, but yeah. Anyway,
Or maybe it's an inclined runway.
no,
or
actually,
something.
yeah, actually, insanely huge engine. Well,
Yeah,
still
but what does a
can.
parachute have to do with takeoff?
Jet or rocket assisted takeoff kind of thing.
Yeah.
Yeah.
Ooh, so like
Okay, booster. Strap-on booster or something like that. Okay, anyways. Have you ever seen like a strap-on booster take off for Blue Angel, like a C-130? Yeah, they actually did that performance years ago at the Prescott Airport. They had a complaint because they burned like a runway and also turf. They had a terrible complaint from airport after that demo, so they stopped it. Too bad.
I know. You should show us a video.
Yeah, it's cool actually.
No, like right now.
Yeah. So suppose alternatively, if your engine is a very high thrust engine, that means at least as high as your takeoff weight. This case, is it true? Takeoff weight for this case is 6,000 pounds, 600 pounds. What's your engine thrust? 1,700.
Nope.
No, I mean, this is not the high thrust engine. But suppose if this is a high thrust engine, you can actually alternatively use this shortened equation, right? So in this case, obviously, this is not valid, but let's suppose if you use this short-handed equation. In other words, you're going to ignore all of those terms in the bracket. In other words, just thrust is the only thing. Drag, no, I don't care about drag. I don't care about rolling resistance kind of information. If the engine's very strong, you don't care about the drag or rolling resistance during your takeoff. Okay, so you're going to turn those into 0. But if you do that, what happens here? If you do that, this is going to give you 1,625 feet. This is, yeah, this is like massively underestimated, too short. This is underestimated. So I guess if you do such a thing for, unless you are talking about high thrust engine, this airplane may overrun. Now in Prescott, overrun is okay. You just ruin some field. But if you do overrun at Sedona Airport, what do you think? Your airplane go down to the body. Too bad. Sedona Airport, have you ever seen that? It looks like an aircraft carrier. Airport is built on top of mountain, flat land. So that's quite interesting. If you take an airplane ride and then take a look at that airport, that's scary. It's like an aircraft carrier landing. Yeah, that's right. Well, you can take the airplane in Sedona. You just pay a lot of money and ride on the biplane. I don't know, one ride is $900, something like that.
It's free if you go with the flight suit. they legally cannot charge you.
Oh, really?
Yeah.
I guess that's true.
Can't pay
Yeah.
people to fly.
Yeah.
Okay. I think you have a flight sim, right? You can load up the data in that flight sim in the RAM. This is Sedona. Okay.
Microsoft Flight Sim.
Any question here? So next page is landing. Of course, like I said, landing, everything is the same. It's just the opposite direction. You're going to slow down, safely touch down, and decelerate to 0 speed. And then only one difference here, I'm going to emphasize, only one difference is this. So landing speed, this is the approach speed, is 1.3 times V stall. This is like a bigger factor of safety. You don't want to decelerate too much, too close to stall speed. That means you don't want to stall before you touch down. Okay, so that's the only thing. So factor of safety is a little bit higher. This is going to trickle into this number. Instead of 1.44, you are going to deal with 1.69. So the landing distance tends to be a little bit longer than takeoff distance. So that's the only difference. So I'm not going to cover example problem here because it's exactly the same problem. It's just a different order. Order is flip-flopped. Okay. All right. So let's move on to page 6. Now we are going to talk about 2 turns. One is level turn. The other one is vertical turn. Either way, we need to talk about something kind of new, something called N. This is called load factor. Okay. N is a load factor. Oftentimes, pilot talk about G of a maneuver. So oftentimes we talk about like a 2G pull up, 4G level, stuff like that. This is going to be how much force is developed over your wing. So if your wing is flimsy, this may dip your wing. Okay, this is a load your wing needs to take, load factor N. So let's just take a look at level turn to begin with. So level turn, one important thing is this is a sustained level turn. You just keep turning and turning and turning and turning without losing your altitude. That's called sustainable level turn. Now, momentarily, your airplane can turn much tighter, but you cannot sustain. You are going to lose your altitude. If so, it's not level turn, sustainable. So we are going to simplify our analysis. It's just only level turn. You're going to once again apply equation of motion in 2 directions. One is the direction parallel to the flight path. One is the direction perpendicular to the flight path, obviously. And then you come up with two equations. One equation is called turn radius, radius of turn. The other one is the rate of turn. So those two are important things. Turn radius. So this is radius of turn. This is the rate of turn, how fast you can turn. Okay. So this is like a degrees per minute or something like that. How much angle you can rotate around the circular motion. Okay. And then one important thing you have to remember is, okay, when you do a high level turn, such as you really want to tighten up your radius, you want to turn really, really quick, you're going to increase your bank angle. That means your airplane needs to create more lift to support your altitude. Lift is increased quite a bit. If the lift is increased, what happens to your drag? Anybody? Drag is increasing. Why drag is so increasing? Because lift is increasing. What kind of drag is you're thinking about increasing? Induced drag is increasing. Drag due to lift is induced drag. It is going to increase. How much? This much. So again, depending on the factor of safety, though. No, load factor. Load factor comes into play. So that means if you create a very strong, highly maneuverable airplane, you're going to do like a really tight turn, fast speed. You are going to actually increase big time the drag. Induced drag is increased. Induced drag is increased. That means you need a more powerful engine. And then engine person says, well, we need to double the engines fast. And then structural guy says, well, our airplane needs to be beefed up, make it. Then aerodynamics guy, that's too heavy. You need to have a bigger engine. Well, we can get bigger engine. Well, we need to make it stronger airplane. It's going to be a heavier airplane. And very easily, your airplane becomes monster. It can never take off. Okay, so let's be careful about that. The downward spiral pattern for design team. Design team need to fight until one of them give in, but whoever gives in, that person is going to suffer. That's the design process. Sure. If aerodynamics person says, no, I'm not going to need any increase of weight, then structures person says, whoa, what should I do? My goodness. Let's find a better material or something. Okay. So I guess positive upward spiral is always good. Anyway, you can only tell by talking to the manufacturing guys. Those are the strongest people because they basically pretend like, hey, we are the only ones who know how to build airplane. And you aerodynamics person, you sit in front of a computer just simulating. You're telling us what to do. Who the hell are you thinking you're doing? And then you need to still convince those bad people. Make them somehow make airplane. Make an airplane, damn it. Kind of thing, right? Good. So, believe me or not, that same thing or similar thing actually happens after you graduate, get a real job. Okay, so get used to it. Yeah. And then everyone is under control by very bad supervisor manager, in which we try to simulate here being very bad professor. Very demanding, not going to support anything, just to give you, okay, we'll make airplane record, I'll give you only 2 weeks kind of thing. And do professional presentation, it's impossible. It's intentional, okay? Because we love you, we want you to be successful. That's why I try to be very bad professor. And then after you graduate, get the real job, you think like, hey, this is nothing compared against Dr. H's class. What are you thinking? This is nothing. Oh God, yeah, this is easy kind of thing. That's how you feel. Okay, anyways, joking aside. So 2 things comes into play. One is turn rate. One is turn radius, okay? Of course, the equation is coming in from 2 equations of motion. Obviously, This is the vertical direction summation of force is equal to 0. In other words, you want to just sustain your altitude. You're not going to accelerate in vertical direction. This is going to give you weight is equal to lift times cosine phi. Phi is a bank angle. Okay. So inverse of bank angle cosine phi is actually the ratio of lift to weight. Lift over weight is called N, the load factor. You are actually creating more lift than weight because you are trying to turn. So your wing is under heavy loading. You're creating more lift than you actually support. You know, when you fly level flight, lift equal to weight. But when you turn, lift is way bigger than weight. Okay, so this is a load factor. So load factor N is alternatively known as a G force. So pilots say, okay, this is a 2G level turn, 3G level turn. They use that kind of word, okay? However, G is already taken as acceleration of gravity. So we avoid it. That's why we use N, load factor, okay? All right, so anyways. So out of the summation of force in horizontal direction, obviously this is F equal to MA in tangential. No, this is not tangential. This is normal direction. So this is, what kind of acceleration is this? This is centripetal acceleration from dynamics. Sure. So from here, you can determine turn radius equation. Turn radius is a function of gravity and also load factor. Okay. And then rate of turn omega is velocity divided by turn radius. So you can get the rate of turn. This is the sustainable level flight. So in order to minimize the turn radius, of course, load factor should be higher. In order to maximize the rate of turn, of course, load factor should be higher. Okay. So this actually goes all the way back from aerodynamics person to structures person saying, hey, you know, I want to do like a really steep turn. Can your structure support that load factor? Then the structure person's answer should be usually be, what do you think? Are you crazy? We're trying to make him minimize weight. You know, you're talking about those things. Again, some airplanes don't need to maneuver, right? In your airplane, you don't need to maneuver. You are happy if you can barely turn around and come back. If so, yeah, I guess the design optimization process is how much you can reduce the weight as long as you are going to carry your heavy payload and barely take off and turn. So turn radius, actually turn radius matters because, right? Because turn radius.
For the two big turns, yeah.
Yeah, that's right. Do they have like a field length limit? As long as you can still see, you can turn like all the way, or I don't know.
I think they give it rules somewhere. It depends on where they host the competition.
That's right, yeah, okay. So this is actually somehow coming to your design. And so what kind of airplane are you guys designing, by the way?
For the
Business jet, right, project.
Ours is a sport aircraft.
Sport aircraft, that means turn radius, rate of turn, that's big things. You probably want to sort of optimize, right? And then I saw like a cargo airplane or very big jet engine. Who are those?
I think me and Matthew Demas are.
That's right. So this one is also kind of important. Okay, anyways, it depends on your airplane. Okay. So drag for turning airplane, of course, because you are going to create more lift. Of course, lift is N times weight. If you're doing like a 2G turn, it's going to be double. 4G turn is 4 times bigger. Your CL is going to be huge. That's not the good news, actually. Bad news is because CL is huge, you are going to have a huge induced drag. So this is K times CL square, or CDI, induced drag, is going to be increased this much. Okay? So this is the portion that you have to include increased drag coefficient. Induced drag is increased. Okay. So next page, let's just take a look at example, yeah? Example is very simple. Okay. Level turn example. Two different airplanes, one on Mars and one on Earth, performing level turns at identical true airspeed, 100 meters per second, and identical bank angles of 60 degrees. How do their load factors, turn radius, and rate of turn compare? This is actually easy. Okay, now one is fictitious, of course, airplane on Mars. Well, this is just the idea of Air Force Academy people. Load factor is, okay, inverse of cosine of bank angle phi. So inverse of cosine 60. 2. So this is a 2G level turn. Okay. So for the 2G level turn, let's take a look at the turn radius. First of all, Mars. Mass gravity is 3.72 meters per second square. So turn radius is equation-wise b squared over g square root n square minus 1. So velocity is 100 meters per second. Gravity is 3.72 meters per second square. Square root 2 square minus 1. If you plug in all of those values, 1,552 meters. So this is turn radius on Mars. Suppose if you do the same turn, 2G turn on Earth, do you think this is smaller or bigger?
Much smaller.
Much smaller because gravity is higher. Okay, good. On Earth, gravity is higher value, 9.8 meters per second square. So if you plug into the same equation, okay, 100 meters per second, this is 9.8 meters per second square.
He's supposed to be squared, right?
That's right, square, sorry. Square, I forgot. Sorry about that. 100 meters per second square, 9.8 meters per second square, g times 2 square minus 1 is going to get you 589 meters, which is significantly smaller radius on Earth. Obviously, because gravity is higher. Okay. What about the turn rate of turn? For some reason, my T looks like F. I don't know why. Okay. Rate of turn. Let's begin with Mars. Okay. Once again, gravity of Mars is 3.72 meters per second square. Rate of turn omega is given as an equation g times square root n square minus 1 over b. This case is b. Okay. So 3.72 meters per second squared, square root 2 square minus 1. Velocity is simply 100 meters per second. If you plug in 0.0644. Unit is radians per second. Actually, if you convert it to degrees, 3.69 degrees per second. Okay, so this is rate of turn on Mars. If you do the same thing on Earth, obviously the gravity is much higher, 9.8 meters per second square. If you plug into the same equation, 9.8 meters per second square root 2 square minus 100 meter per second. This is going to compute 0.1697 radians per second, or 9.72 degrees per second. So this is much higher rate of turn on Earth. Okay, this is a very simple exercise, just comparing Mars and Earth's performance, radius of turn and rate of turn. Okay. Next page is vertical turn. This is actually contrary to the level turn. You're going to completely loop vertical plane, 360 degrees loop. Okay. Again, it's simplified, so you are not going to have any directional motion. Just the loop is 100% vertical. Okay. So obviously you have to deal with the gravity. This loop is going to be performed against gravity. Okay. So this is the model of vertical turn. This is the simple vertical turn model. Okay. This is a purely in vertical plane, 360 degrees turn from the original flight path. This is just a loop. Okay. So the maneuver will start with a pull up. This is called pull up. So this is going to pull up from the straight level flight. You're going to gain the altitude. This is the 1/4 of the looping maneuver. Airplane's attitude is completely 100% vertical up. Okay. And then after that, you are going to actually reduce the radius. Okay, because you're going against the gravity, you're going to keep losing your airspeed. So initial radius is going to be reduced, and you reach the top, and then you're going to pull down, which is complete the other half of the loop maneuver. Okay. So the equation, this is the equation for the condition of pull up. So you're going to actually start with a pull up. Then this is pull down from the top to bottom. This is on the very side. So this is the velocity vector is vertical. In other words, airplane is flying like this, right here. Okay. So you have like 1 and 2 and 3 equations available. Okay. And then let's combine all of those equations. This is the turn radius of vertical turn, and this is the rate of turn of vertical turn. Okay. For the case of pull up, pull down, and then this is the case that airplanes completely, velocity is completely vertical. Okay, so those are the 2 equations. Okay. Next page. Wow. This could be, I don't know, this could be a final exam that the Dr. Ashworth make.
No thanks.
This could be like, okay, well, here's a problem for your final exam, Dr. Ashworth usually does. So go ahead, solve it if you know about airplane. Well, let's take a look. The procedure for performing a loop in the T-37 begins with diving the aircraft to reach the entry airspeed, which is 250 ks. Oh, by the way, what's ks? Indicated. Eyes indicated, okay? So this is 250 knots indicated airspeed. Altitude 15,000 feet. Okay. Why do we have to make it indicated? But anyways. So you have to convert indicated to true airspeed. Yeah, conversion process comes in. Do you still remember that? Indicated to equivalent to indicated to calibrated to equivalent to true. IST. Yeah, you have to do this. I don't know why, but you have to do this. This is a good reminder for that conversion process. And then putting straight up with, oh, this is 4G, vertical pull up, 4G turn, okay. As the nose comes up, the speed begins to bleed off. That means you cannot maintain the initial speed, 250 ks. This is going to begin like decreasing, okay, as you pull up. But you continue at about 200 ks or a little less, okay, you start to feel a tickle in the stick. That's not a good sign. So as you start feeling a tickle, you're going to gently push back. Try not to stall your airplane. That's right. And it occurs before the drag due to lift gets too large. If you pull into a heavy buffet at this point, that's it. You cannot loop. But if not, if you're a good pilot, you just keep talking with your airplane. Hey, don't stall, man. Just keep going, kind of maneuver. Okay. Then you're going to gradually, release out G. So G is reduced from 4G to 3G as you're trying to continue looping. And then you're reaching at 18,000 feet, 180 ks, which is right here. You begin climbing, you reach here. So this is the load factor starting with 4. So this is 4G pitch up turn, pull up. Then you keep going, and then you're reaching here. This is like a load factor 3, reduced load factor, and then airspeed you lost from 250 to 180. Okay. So from here to here, you can determine the radius, okay, rate of turn also. And then starting from here, you try to reach the top. You just continuously losing your airspeed, and then continuously losing your radius and rate of turn, but you reach to the top. As you reach to the top, load factor is 1.5, velocity or airspeed is 100 ks. Now you are going to start pull down. Complete the other hub. Okay, that's what it says. So as the pitch attitude exceeds 90 degrees, you throw your head back. Well, you're flying like this, you throw your head back. That means you're watching your ground, isn't it?
I think you look upwards to look at the horizon.
You still look at the horizon, that's right. Yeah, as an engineer, we can never understand those language, but you have to deal with it. Okay, so look to find the horizon. Good. And then pull down to it, being careful to keep the wings level against the horizon. That's what it is. You need a horizon, making sure you are still turning vertically. Okay. If you do everything correctly, good luck, but you will make it to the top of the loop with n equal to 1.5, 100 ks, 19,000 feet altitude. Then as you continue to pull down inverted, the speed builds up, you're going to essentially accelerate, go back to the pressure and load factor required to stay on the tickle. I see. Now you're going to go back to load factor 4, you go back to level flight, you complete your maneuver. That's right. So, what is the question anyway? But from the cockpit, T-37 loop flown as just described looks like a circle, but it's not. What would it look like from the ground or from another airplane? That's what you want. Calculate the turn radius at 3 points, and then to estimate the actual shape. Okay, so that's what you want. So let's just take a look at this. This is the solution, by the way.
Wow.
Yeah. So you are starting from here, load factor 4 pull up. So you can determine the radius. That is going to determine this flight, this portion of flight, right? You start from here, coming in and pitch up, pull up, load factor 4G pitch up, okay, pull up. And then you hit here, okay? And then right here, you are going to reaching like load factor 3, velocity or airspeed 180 ks right here. And then you literally trying to reach the top right here. And then obviously the radius, you're going to be much smaller radius because you're flying slower. okay? And then after that, pull down to get out of it, okay? So this is how it looks like. And you can actually compute that, okay? So let's just compute that. Now, computation is kind of, why do you need to make it so kind of confusing? But Kias is given, okay? So let's take a look at it. So at the beginning, velocity is equal to 250 Kias, knots in indicated airspeed, okay? So let's assume there is no positional error. In other words, you don't have to calibrate because you have a very beaten up pitot-static tube or anything like that. You install the pitot-static tube in wrong position, you have to correct it. You have no such a thing. So let's assume that this is about 250 kCas. You know kCas? Calibrated, okay? Because no position error. No kCas, based on standard suitable density and pressure, you have to do F factor correction. So 15,000 feet with 15,000 feet, this is pressure altitude. Okay, so the pressure altitude is given with 250 kCas. Let's find out factor F. What's F factor F? Where do we need to go back and take a look? Unit A1, A1 or A2 or something like that. Let's go back. Oh, this is not the program I made. This is a program made by Air Force Academy people. So let's just go back to Unit A2 and the ICT F factor. Where is it? There's a table, yeah.
I think the table.
Yeah, I think it's in the other one.
The other one.
Yeah.
A1?
A1.
Okay. So let's take a look at the note A1 and then find out F factor.
Maybe it's in B1.
Okay. Here we go. This is F factor, compressibility correction F factors. So the pressure altitude given 15,000 feet, right? And the kCas, what? 250. This.
9.
Yeah. So this is the F factor. You need to pick it up. 0.987 F factor. I'm going to pick up 0.987. Therefore, what is the equivalent airspeed? The equivalent airspeed is F times BC. Calibrated airspeed 250. So 0.987 times 250 kCas is 246.8 KEAS, not the equivalent airspeed. Then the true airspeed. Equivalent times ratio of density sea level over the density of 15,000 feet. Let's assume today is a standard day. 240. 246, yeah. Why am I saying 245? 246, yeah, 0.8 KEAS multiplied by density ratio square root 0.002377 0.001496. This is, by the way, standard density at 15,000 feet, assuming today is a standard day. This is a ratio, I just omit the units. So this is going to be 310 kTAS, knots in true airspeed. That's just to convert 1.69 feet per second over knots. And then you get, 523.6 feet per second. Why do I have to do it? I don't know. This is like one tedious step. You probably have nothing to do with this problem itself. I don't know why, but anyways, this is a problem given by Air Force Academy. It's not my fault. Okay. So this is the airspeed, okay, at the pull-up. So let's find out. At n equal to 4 pull-up, you're going to create a MATLAB code to do computation for that. That's a good idea. So this is a 4G pull-up, okay? And then you have a radius, which is b squared over g times n minus 1. So you just simply plug and check 523.6 feet per second square. G is 32.2 feet per second. N is 4. 4 minus 1. This is going to be 2,838 feet. This is the radius, almost like 3,000 feet. That's why you are going to start with 15,000 feet, go to about 18,000 feet. Okay? So maneuver is looking like this. So you are going to start from here, and you're going to end up here. Radius is 2,838 feet. So if you start with 15,000 feet, you end up about 18,000 feet here. Okay. So now, oh my goodness. Now what? Now, anyways.
Possibly if you just give us the velocities, since we
Yeah.
already know how to do the calculation.
I think we know how to calculate that.
So about 3,000 feet radius, then you are going to have 180 kias. How come you just keep giving us kias? And then you go through the same process, same iced tea, same iced tea. C is capital, sorry. So same process involved. Indicated to calibrated to equivalent to true. You are going to convert this into 398.9 feet per second. Okay, sorry about that. I'm going to skip those process. It's a waste of time. You just do exact same thing. Anyways, for some reason, Air Force Academy people actually give you kias. Why? I will give you this instead. Anyways. Yeah, it sounds like, they're trying to flunk you at the final stage. This is like an evil professor making final exam. So this is at the side of the roof, okay? Side of the roof means right here. You know this is about 3,000 feet radius, okay? Not quite, but 3,000 feet radius. So 15,000 feet you began, you ended up in 18,000 feet side of the roof. Load factor 3, this is airspeed 180 kias, okay? So what is the radius here? Radius is going to be super small. Okay, because you reduce the velocity, b squared over g times n. 5 more minutes. So if you plug in, velocity is 398.9 feet per second. This is square. Gravity 32.2 feet per second square. Load factor is 3 now. It's reduced. This is 1,647 feet. So this is the radius now. It's shortened up. Okay. So this radius now is going to be This radius is now about 1,600 feet. Smaller radius. So you fly up, and then radius is like really small. Then you reach the top, okay? Next step. So you reach the top, reach the top what? Ooh, did I lose anything? Ah, reach the top, okay. At the top of the roof. This is pull up, pull down, sorry, pull down. So pull down, you have, yeah, load factor is now 1.5, and the velocity is given 100 ks. 100 ks. Again, same process. This is what? 226.97 feet per second. Okay. Again, same IST process. Okay. So the radius now becomes b squared over g times n plus 1. So if you plug that in, this is 226.97 feet per second. This thing square, 32.2 feet per second square times 1.5 plus 1. Compute 640 feet. Whoa. Okay. So those are the radiuses at the different location of this loop maneuver. Then if you plot it, this is how it looks like. Okay. This is the maneuver pass. Any question? So this is the end of unit C3. So starting from next week, we are going to continue on C4, which is BM diagram, which we're going to cover a little bit of structural side. And then C5 is the example of performance computation. So project phase 3 is coming near. So let's be ready for it. Okay. Any questions? Good. Have a good weekend. See you guys back on Tuesday next week.
What? Oh, yeah, right. You have an exam now to take.
Meet your exam. Meet your exam.
You grab some lunch.